study from the University DTM lab. The paper I will review is Identify Technology Opportunities via Technology Landscape from the Perspective of Convergence Degree, a case study of computer vision and wind power. First, this is the bibliographic information for the paper. This study proposed a novel framework for constructing technology landscape from the perspective of technology convergence degree so as to identify technology opportunities. The content are the same as structure of the paper. First is introduction. As technology systems get increasingly complex, technology convergence is emerged as a key driver for identifying technology opportunities. So efficiently identifying technology opportunities through convergence is crucially for enterprise to optimize their R&D strategy. Therefore, many studies have attempted to identify technological opportunities based on technology convergence. Existing approach focus on predicting technology convergence but are limited in assessing its degree and identify technological opportunities. So this study proposed another framework which can conduct a technology landscape based on convergence degree to identify technology opportunities. Computer vision and wind power are increasingly converging, so they play a significant role in improving industrial efficiency and safety. But previous studies have rarely analyzed this convergence quantitatively from a technology convergence perspective. So a new framework is needed to quantify the degree of convergence and identify technological opportunities based on that level. Technological opportunities arise not from isolated technologies but from the convergence of different technological fields. However, most existing research has not precisely measured the degree of convergence. Therefore, an approach that identifies the opportunities based on the degree of technological convergence is required. A substantial portion of technological opportunities arise from the recombination of existing technological elements. The concept of a technology landscape is used to explain this process. Prior studies have constructed technology landscape using patent data, DTM, and trees. DTM captured the evolutionary pattern of technological topic, while trees identified opportunities based on technological evolution principle. Therefore, integrating DTM and trees enable the multiple dimensional classification and recombination of technological elements, leading to a more systemic identification of potential opportunities. Next is methodology. Figure 1 is the proposed research framework. This study proposed a systemic framework to identify technological opportunities in the CV and wind power field from the perspective of technology convergence. First step is data collection and pre-processing. This study collected patent data on CV and wind power from the DII. Subsequently, the data underwent processing procedure to construct a data set, providing the foundation for semantic network analysis and measurement of technological convergence. Next is technology convergence degree measurement. In this step, to measure technological convergence, technology topics are extracted using what topic. Patent abstract are embedded, use the BOT model, then cluster to derive topic. Finally, C, TF-IDF, and MMR are applied to select representative keyword for each topic. Next, the semantic network is constructed based on the inclusion relationship between patent and technology keyword. In this network, node represents patent and technology keyword, and edge denotes the inclusion relationship between them. Then a GCN is applied to the graph structure to learn characteristic vector of patent and keyword. By integrating structure relationship, the GCN produces more refined representative embedding. And then cosine similarity is calculated between patent vector and technology keyword vector to measure semantic similarity. For each patent, the maximum similarity within the CV keyword set and the wind power keyword set is selected as the CV intensity and wind power intensity respectively. Patents with high value in both dimensions are interpreted as having a high degree of technological convergence. Next is the technology landscape development based on technology convergence degree. First, the convergence curve is fit to determine the threshold, and the patent exceeding this threshold were selected as high convergence patent. Then DTM is applied to this patent to extract technology topic are analyzed their temporal evolution. The corpus is divided into time slice, and topic coherence were used to determine the optimal number of topics. And then technology elements derived from DTM and classified according to trees technology evolution trends. Based on the 8 pattern of technological system evolution present in Table 1, topics were mapped to the corresponding evolution dimension through expert evolution. As shown in Figure 3, these mappings are used to construct a technology landscape that visualizes structural relationship among technology elements. This enables a more systemic identification of potential technological convergence opportunities. Next is the technology opportunities identification based on technology landscape. Based on the technology landscape, technological opportunities are derived using domain expert knowledge and innovation theory. First, multi-dimensional technology elements and deposit and recombine to generate potential combination. Then the generate schemes are structurally analyzed and evaluated in terms of technological feasibility and innovation potential to select high-value opportunities. Next, to verify the effectiveness and predictive accuracy of the proposed method, the identified technology opportunities were compared with existing patents. The evaluation procedure were conducted as follows, and the final score for each technological opportunities were calculated used an equally weighted average method. Additionally, associated keywords were used as search query to examine the existence of identical or similar patents. The next is result. Patent data related to CV and wind power were collected from the DII database. A total of 22,100 patents were retained for final analysis. Using per topic, certain initial topics were identified, and after coherence validation, 12 final technology topics were confirmed for both CV and wind power. As shown in Table 2, the key technology keyword were organized to define the major topic in each domain. Patent and technology keywords were vectorized to construct a semantic network and obtain graph structure data. The GCN model demonstrates stable performance. For each patent, the maximum cosine similarity with the CV and wind power keyword set was calculated to construct two-dimensional convergence coordinate. As shown in Figure 4, patent located near the diagonal exhibit strong technological intensity in both field, and the degree of convergence between the two domains has gradually increased over time. Based on the fit convergence curve, patent with CV and wind power intensity above the threshold were classified as high convergence patent. A total of 1,518 patents were finally selected. These patents were divided into 4 time periods, and DTM were applied. For each topic, the top 20 keywords were selected as representative term as present in Table 6. Technology elements identified by DTM were mapped onto the A-trees technology evolution dimension to construct the technology landscape. As shown in Figure 5, convergence topics were connected to multiple evolutionary dimensions, forming a multidimensional structure. This enabled the recombination of key elements across different dimensions to derive new technological opportunities. Next is technology opportunities identification and validation. Based on the technology element extracted by DTM, technological opportunities for digital and intelligent transformation in the wind power industry were identified. According to the proposed methodology, an expert panel evaluate the identified technological opportunities. The evaluation criteria, novelty, feasibility, and application potential were systematically applied to calculate the score. Next is conclusion. This study proposed a novel approach to identify technological opportunities based on the degree of technological convergence. By integrating both topic and GCN, a quantitative coordinate system for convergence strategies were established, and by combining DTM and trees, a structured technology landscape was constructed to derive opportunities. However, the study primarily relied on patent-based information. Focused on high convergence, patent may underrepresent early stage innovation and the involvement of expert judgment in trees-based classification and effect reproducibility.